Now, when Nick says a deep dive, he also boxed me in a half an hour. So keep that in mind that when we say a deep dive, we're going to fly by this thing about 10,000 feet, okay? One of the biggest things whenever I talk to anybody, I think we in the ag industry, we all take terms for granted, right? That everybody should know what we're talking about. Number one that I think about that we all take for granted is ET, what it is, and how we account for it. So part of this, I'll even throw in there how we can design pivots based off of ET demand. So, and how we measure some of that water. My background, like I said, my name is Jake Beam. I work for Franke Manufacturing. I've been there for 22, 23 years. I've worked in lots of parts of our business, now on the sales side. But in the past 4 or 5 years, I've really taken a deep dive into soil moisture and plant relationships and pivot design, that kind of stuff. So that's kind of the background in some of this stuff. Some of the images you'll see, I teach a lot by images. Some of the images you'll see, please don't take offense to it, but they are meant for junior high level. I teach some junior high level courses at our local public school. But this is the easiest way I can get people to understand very quickly at a very high level what it is we're talking about and why it matters. So don't take offense if it seems very, very dumbed down, right? We're going to start off, we're going to talk about the operation of a pivot. Basically how a pivot operates and how it moves to the field. We're going to keep it very high level. We're not going to talk about swing arms or end guns, that kind of stuff. Just basically how a pivot moves. We're going to talk about sprinkler design. Why we do what we do. Why a sprinkler puts out a certain amount of water in different parts of the field. And there's actually science behind some of this stuff. Pumps, very high level, how a pump works, right? Because it actually makes a difference when you guys are out in the field. Then identifying infield issues. This is boots on the ground. How many times does a grower actually see their pivot during the middle of a corn production? Once it gets to tassel, they'll drive by. Yeah, they'll see it squirting water back in the corner. But how many times do they actually go out in the field? Unless they, there'll be a select group. But most of the times, it's this group of people who are out in the fields and can identify issues early on. And if you guys become those irrigation experts for them and help them identify some issues, it'll benefit everybody, especially the grower at the end. So basic irrigation operations. Okay, so if you look at this over here, there's this little pivot over here, right? And it's a little 6-7 tower machine, and we're going to talk about how it actually works. So at the main control panel, it's right there at the center of the machine, right? Sometimes it can be remote, but for the most part, we're going to talk about this one. It's right at the center. Every mechanized irrigation machine works the same way. We control the speed of the last tower. Okay, that's how we're controlling how fast the machine goes in a circle. Okay, that's how we're controlling how much water is being applied throughout the field. So the main control panel is telling the very last tower when to run. It can control basically a contactor out there, tells it start and stop. Okay, so we're controlling the speed of the machine. Everything behind that are the inner towers, and they're quote unquote the slaves to the outer tower, right? It's all they're doing is they're keeping up with that outer tower. So they've got alignment boxes on them, and they're just trying to keep as straight as they can, and they're just keeping up with that outside tower as it moves through the field. Now there's a tower box to each monitor, or each tower, and it monitors the alignment, and it controls when that machine starts and stops. And I'm going to speak Ranke language, but most of them are all the same way, okay? There's 3 different types of boxes. So there's an A, a B, and a C when it comes to the Ranke world. But the last tower is called the C box. Now, the only difference between the C box and anything else is that it's wired up to where it's monitoring that main control panel, right? It's wired up so when that main control panel says go, it starts to move. When it says stop, it stops. Okay. Now I skipped one. You're going to notice I went from the C box clear out at the end, and now I'm going back a couple. And these are called A boxes. These are just monitoring alignment. Okay, that way. As soon as that tower out in front of it gets a little out of line, the other one catches up and they just kind of serpentine through the field, right? And they're just working their way around. Now you'll notice I skipped the second to last tower. That's the next last tower box. It's called the B box in our world. This just has what's called an overwatering timer, okay? So if that last tower, if anything happens to the drivetrain, right? If anything stops that machine from running, it gets stuck. Anything that happens, that second to last tower has a timer in it. And if it doesn't move within a certain amount of time, it'll open the safety of the machine and shut it down, okay? You'll hear a lot of people talk about the overwatering timer. Almost every machine, if you start the machine in the other direction, it'll reset that timer, okay? So these are little things that if you guys ever hear guys talk about, did you start it in the other direction? No, that's why they're asking. They're identifying issues by asking you very simple questions. So that's basically how a machine works, right? So as the in tower starts, everything else keeps up, and we can control the speed of the machine, right? And that's about the most we're going to get into how a pivot works. I want to save some time at the end if anybody has any questions, okay? Now, the biggest thing, understanding water demand. Now, I love the fact that we've been talking about ET all day long, because ET, ultimately what ET is we're measuring water, okay? And it's a real tangible number. We can talk about gallons even, about how many gallons are leaving the field based off of ET. So like I said, I have some very generic diagrams here. If an acre, we all know an acre is 43,560 square feet, right? Well, to get a close enough box, we're going to call this 310 feet by 140 feet. Now I've got an empty box up here, okay? And I've got this water hydrant. If I fill up that water hydrant 1 inch deep of water, we are now talking about 1 acre inch of water, okay? And that's 27,154 gallons of water, okay? So that's what an acre inch of water is. So if I put on 1 inch on 1 acre, I'm going to use that many gallons. Now, most of the time, what we talk about is ET, right? And so when we're talking about ET, most of the time you'll find out what the maximum ET of a plant is, and this is how we should be designing pivots. So if I'm or any irrigation system actually, if I have a maximum ET of whatever crop I'm growing of 0.3 inches a day, okay? So now I have this same box here, and you can look over there, now my depth is only 0.3 inches, not 1 inch, right? And I do the same thing. I fill this thing up. I can still measure that amount of water, right? Now, 0.3 acre inches is only 8,146 gallons per day needed per this acre. So I've heard a lot of talk about NRCS agencies and all the different things that come about with those guys. The hard part with NRCS agencies, you know, they set federal minimum standards, then state level, then local level, right? Some local levels will say you have to have, you know, a soil moisture probe for every 40 acres irrigated. Some will say 1 per pivot. Some will say you have to maintain at least so many GPM per acre on design. Okay, so what they're talking about is we know in this part of the world that your maximum ET is this, so we know you have to have this many GPM per acre to catch up. So if that same field, I have 0.3 acre inches needed, and it's that many gallons per day, and there's that many minutes in a day, okay? To fill up this 1 acre, I need a pump that goes 5.7 GPM. Okay, so all we're doing is we're working stuff backwards here because I want you guys to kind of understand why pivots are the way they are. So in order to maintain 0.3 inches of ET per acre, I have to have 5.7 GPMs per acre. Okay, because all we're doing is measuring water. To maintain proper irrigation on 100 acres, okay, so now I'm going to go from 1 acre up to 100. I need a pump that can maintain 570 GPM, right? I just now sized a pump for a pivot based off of ET. Okay, now just keep in mind, this pivot running all the time, right? So there's all sorts of other things when you talk to a Reinke dealer or an irrigation specialist, when they're designing you pivots, they'll take into account if you have load control, if you know, if you're sharing this pump or this pivot with another pump, right? We'll take all that stuff into consideration. But for today, we're going to talk about just this one little application. So for a total of 100 acres, I need 570 GPM, okay? Now we're going to talk about this same pivot here. Okay, I have 6 spans, they're all 175s, and it covers 79.51 acres. Span 1, actually, we're going to talk about each span as its own outlet, right? We're not going to talk specifically about each nozzle, but let's just talk about each span individually. Span 1 covers 2.21 acres, okay? If I know how many GPM per acre, I can tell you that that same mathematical part, span 1, 5.7 GPM per acre is what I needed to match 0.3 ET. There's the acres. So I'll have 12.6 GPM coming out for span 1. Okay. Now look out at span 6. It covers 24.3 acres. That circle's so much bigger, right? Since we're covering more acres and I have to maintain GPM per acre, I can now tell you that there's 138.5 GPM coming out of the end tower. So you guys heard this morning all about infiltration rates, soil types, all that kind of stuff. This is when it really comes into effect about designing machines. We want to make sure that we don't surpass the infiltration rate out at the end, right? We can't just put on as much water as we can. So these are some things we got to watch out for. But ultimately, the center point, or the closer we get to the center, will put out less water than we get to the end, right? It's just to make sure we're putting on the right amount of water in the right spot. So hopefully this video works. Thanks to, if you guys know Josh Moser with Comet Irrigation, he sent me some of these videos. I can look at this picture right here, and I can tell you which side the center point's on, right? Now, this is a little over-exaggerated version of this. This is just for demonstration. But on this video, the center point is to the left side. The end of the system would be to the right. So if you're ever out in the field and you don't see a nice steady stagger from low flow to high flow at the end, you have an issue out in the field, okay? Or we're not putting the right amount of water in the right spot. Those are things that even if you're not in the irrigation industry or the mechanized irrigation industry, these are things you guys can point out real quick for growers, right? They will see this in the yield monitor at the end of the year, right? If this isn't the right way. If it was the other way, center point to the end boom, we would have major water application issues out in the field. And this happens a lot with inexperienced people who are putting on sprinkler packages. If you ever have a grower who thinks they're going to put on their own sprinkler package, a lot of times they will not get this right if they don't follow that sprinkler chart step by step. Okay, so that's why we nozzle things the way we do. That's why we put on a certain amount of water as we move out. And like I said, this is going to be a very high level, right? This is going to be junior high stuff. So we're going to talk about pumps real quick. Almost all pumps in the irrigation industry are centrifugal pumps, right? And they come in all sorts of shapes and sizes. The one on the left there is like a deep well set. The one there in the center, the blue one, is going to be more for like surface water pumping. The one on the right is a submersible. If you live out in the farm grounds anywhere, that's probably the type of pump that's pumping your well water, right? If you pull it up, that's exactly what it looks like. But they all work off of the same general purposes, or the same general idea. And it can be seen here. If nobody's ever been to a mud drag before, you probably never really lived your life, right? But you can see the effects of how a pump works based off of this picture here. If this truck was going very slow, the mud would just fly up a little bit, right? It may stick to the edges of the tires and it just barely comes off. When he stomps on the gas, all the mud and water that's stuck to those tires flies out as fast as possible, right? And you can see that. I mean, I don't know if he's got windshield wipers, but I bet he can't see very well where he's going, right? So, but this is basically how a pump works. Here's a cutout. This pump turns on and that impeller starts turning. The water comes in through the impeller eye. Those vanes throw that water out as fast as it can. Okay? It builds pressure and then it goes out the top through the outlet there. Now, keep in mind that most of these pumps, unless you have VFDs, and that could be a whole 4-hour session on VFDs, but most pumps, once you turn them on, they're on, right? So that impeller's spinning at the same speed no matter what's going on. Okay? Now, depending on how much flow, you have different pressure, and that's known as a pump curve. And this is going to be a very, very down-to-earth pump curve. Okay? This is the green line there, basically is a pump curve. Now, the y-axis, going up and down, that's how much pressure is being generated by this pump. The bottom axis, or the x-axis, is how much flow. Okay, so there's pressure and flow. 4 is what's known as a deadhead pressure. I want everybody to understand this, that if I turn this pump on, right, and that impeller's in there spinning, and I shut a valve off, is that impeller still spinning? Yes. Is there flow? No. If I shut the valve all the way off, there's no flow, right? I completely shut off, but that impeller's still spinning, so it generated a lot of pressure, okay? So that's all the way on the left-hand side of this pump curve, okay? We didn't change anything about the pump. We just changed where we're at on this curve. Now, the other end, if I open a gate valve, right, and I'm dumping it's flood irrigation, there's very little pressure, but there's a lot of flow. But that pump is still spinning at the same speed, right? We didn't change anything about it. So just understand that if we can control the pressure and flow based off of different things we do on pivots, but it all has to fall on that green line. Now, this will make a big difference when you guys are out in the field. Okay, and I'll show you a couple examples of why this actually matters, even if you're not in the pivot world. Okay, so if I have a pump that was pumping 10 gallons per minute down there, it would generate about 32 feet of head pressure, right? And so you can kind of move all over in here, and that's just basically how you find out where you land on that pump curve, okay? So what all things affect where we land on this pump curve? Well, any changes in flow affect pressure, right? So if I have more flow, we're going to fall farther to the right of this pump curve. End guns, most end guns on a good design can account for 10 to 15% of the flow. Okay, so if I shut off my end gun, we're going to slide to the left. Our pressure is going to go up. I turn my end gun on, our flow increases, we're going to go to the right. Okay, so this is why sometimes you may see pressure changes on a machine. A swing arm corner with an end gun could be 30 to 45% of the flow. Okay, so these are major things that have to be talked about with growers, especially if you guys are talking to them about things. And if you guys hear them say, hey, they're thinking about adding a swing arm to a machine to pick up extra acres, make sure they're talking to irrigation experts. Make sure they understand pumps, pipe sizings, all these things, so they don't get themselves in a bad spot just because they think they're going to pick up more acres. Wrap spans, if you guys don't know what wrap span is, we can basically bend a whole machine. We can shut things off behind it, right? These are all things that can change where we land on these pump curves. And pressure changes, they can affect flow, right? So you think about taking a shower, right? You guys up on the top floor here, probably a little bit lower pressure up on the top floor compared to the ground level here. You're gonna have less water that comes out because we're not pushing that water as hard. So that can actually change our flow rates. Pressure regulators help with that, okay? So if you have guys out there and they don't have pressure regulators on their pivots and it's going up and down hills, they're pushing water out in places they don't know, okay? Pressure regulators do help. In fact, I would highly suggest them on every machine, especially anything that changes flow rates. Okay, so now that we know how a system works, a pivot moves through the field, we know basically how we design machines, and we know very high level what a pump does, right? Whenever we design machines, and we're going to design the most efficient machine possible, we're going to make it flow as much water as possible at the lowest amount of pressure, right? We're going to be as efficient as possible. So I'm going to try to design these things exactly where I want them to operate as far as pressure and flow goes. If we get outside of those bounds, some bad things can happen. That's kind of what we're going to try to identify some stuff here. Uniformity. Just identify what uniformity is. It's how evenly we dispense water across the entire field. Okay? So if you look at an aerial image like this, what stands out? Lots of things should stand out here, right? Yes, you should be able to see wheel tracks of a pivot. That's not out of the normal. But I don't think there's 70 wheels or wheel tracks on this pivot, right? Okay, so these are things, and just as an aerial image, I'm going to guess this looks like a sandier soil, right? It looks like it's dried out pretty easy. So where we put water in some of these soil types really matters, and they stand out in different locations more than others. So these are the types of things that you can look out for. Circle shapes tend to be, I'm going to say tend, right? This is very generic. This isn't things you have to stick to, but circular shape issues tend to be sprinkler issues, okay? So in this type of situation, there's probably all sorts of things going on with this machine, but this is a good aerial image that I got sent to me that I would have lots of questions about what's going on. Now, however, I do know what's wrong with this field. Okay, I don't know if you guys can see, hopefully you guys can see in that the wind is not blowing here. It looks like that should be a wheat field in Kansas, the way the wind's blowing there, but it's actually a cornfield, okay? So ultimately, you can see the pivot tracks going there. So we know the direction of this machine, right? We know it's going in this. Would you guys consider that a circular shape issue? You guys can talk here, it's okay. Yes, it is a circular shape type issue, okay? Look at the center point of this machine. Okay, even worse. Okay, so what stands out? Obviously, we should not be able to see bare dirt through a canopy. Right? We should not see what looks like wind blowing through a cornfield. Like I said, circular shapes tend to be sprinkler issues. The cause, improperly designed sprinkler package that exceeded the sprinkler spacing limitations. Okay, sprinklers on a pivot they have to overlap by a certain percentage, right? One sprinkler has to overlap the next one and hopefully at least touch the next one or close to. If we exceed that, we're not getting proper overlap. And here's what you'll see. I mean, this picture back here is a perfect example. Yes, some of the stuff in between got water, but not the right amount. Okay. I actually know what happened here. The grower bought a used pivot from a neighbor, moved it in, and took the same sprinkler package off his old machine and put it right back in. Okay. Everybody shakes their head. Yep, shouldn't do that. But if you don't know, like this is education we got to get to the growers so they don't make these mistakes. Okay. Pump and pressure issues. Here's a perfect example. I'm designing a machine. I wanted to operate 1,000 gallons per minute. I needed to generate 275 feet of head pressure. I'm designing it to be as efficient as possible. Okay. How efficient is this machine? Okay. Has anybody ever seen an end gun where the booster pump quits working and it's blowing on soybeans? What happens? Yep, they all get smashed down, right? These are high impact sprinklers. Okay, they should be thrown so far out there you can't even see them. Okay, but I designed this machine to be as efficient as possible. That big leak you guys saw there, what about right there at that boot or at that gasket, right? All these extra flows that are being generated here that we didn't account for moved us so far to the right, we can't generate the right amount of pressure. And it gets worse the farther we get out. The farther we get out, the worse it gets. And then you'll get out here and look at that end gun there. Right? So these are types of things that I know growers, I've heard it from growers all over the place. My father-in-law is a grower. He lives right across the creek from me. And he'll tell me the same thing. I said, Lyle, did you know you got a boot leaking out there? What do you think his response is? Yeah, squirting water. It'll be fine. It's not fine. Not if that thing was designed right. Okay? If that thing was designed right, that is not okay because we are robbing water from one part of the field and blowing it right in the wheel track, the worst spot in the field to put extra water, right? So these little leaks, these little things, we're talking about water management. We're talking about inches of water we're trying to navigate through a foot of soil for potatoes. And we have stuff like this out there. Some of the stuff is stuff that you guys can help, teach growers why it's super important that we do some of this stuff. Okay, so that was circular issues. What about this? Can anybody see what's wrong with this machine? Overwatering, where at? Okay, see those wedge-shaped pieces there? I don't know if you guys can see that. That's why I try to, put some indicators out here. Not only that, but look at where each one of these pieces are at. This is not okay, okay? There is definitely something going on there. Usually what happens when we have wedge-shaped issues, it's a mechanical issue on the system itself. Okay, it doesn't usually have much to do with sprinklers. It's more mechanical issues. So the ultimate cause of this one, we could have a whole discussion someday about swing arms. But this swing arm, if you look down there in the very bottom of the machine, this machine had a swing arm on it, right? It had a corner machine. Ultimately what happened is there was a mechanical device in there. The swing arm was slowing down the parent machine when it was trying to extend, and it was causing overwatering every time it got into those corner areas. Okay. Now, some people may say that maybe that's really what their application rate should be. It looks good, right? But if he's trying to get around, right? If he's trying to get around a certain amount of time, he's actually going to overwater those corners and underwater everywhere else. Okay. So wedge shapes tend to be mechanical issues. All right, here's a good one. This one is one that I love these kinds of talks because this actually happened over some supper and some drinks one night with a local grower by Deschler. Okay, here's one of his fields. I got this off of his climate. This is a yield map. Does anything stand out to you? Other than you could probably pick out every soil type and everything else on this map. Is there anything pivot-wise that stands out to you? Anybody on here? Yeah, and you got to be a little careful with that. He put in a couple polygons over there so you can kind of see the colored polygons. Those are just polygons he laid over in climate view. I just took a screenshot of it. Okay, maybe a pivot issue. Okay, remember, wedge shapes tend to be mechanical issues. What about that wedge right there? Anybody see that wedge? Okay, don't forget this is yield data. Okay, here's an interesting, I love this one because I've never even thought about this. Okay, off of his climate, here's what he got for field health. Okay, here's his field health status. This is on August 5th. Okay, August 5th, everything looks pretty good. I go to August 15th. You can see just to the left of, sorry, I'm going to reference pivots here. 0 degrees is straight north, okay? Just to the left of straight north, you can start to see a few more yellow spots appear. August 25th. 20 days. 20 days, we went from a field to look pretty good to that, all in 20 days, okay? He ran out of nitrogen, John says. Anybody else got an idea? A what? I'm sorry. A tar spot? Nope. By the way, this is in Nebraska. This is a cornfield. This is pretty or typical corn production. This should all look pretty uniform, right? It's up by Shickley, Nebraska. If anybody knows where Shickley's at. Perfect. Issue. The sack got stuck in the northwest corner previous 2 passes. Okay? The swing arm got stuck up in that northwest corner. How do you think the grower fixed it? Sped it up to 100% because that was going to fix his issue. What did he just do? Yeah, and absolutely, in his eyes, he fixed the problem, but he doesn't know how pivots work. He's ran pivots his whole life. He never took this into consideration. The grower decided to speed up the system through this area for the last 2 passes of the year in August on corn. Okay? Sorry, last 3. He made 3 1-inch applications. I went back through and looked at his stuff. He made 3 1-inch applications going through here. Okay? His minimum depth for this system was 0.12 inches. So when he should have been he put 3 inches of water across the rest of the field. In that area, he only put on 0.36 inches. In 20 days, he took probably 100 bushel cut on that corn crop. Think about all the inputs that he put in there that he lost, right? All because of not being informed of how things work. Now, just a little inside information for this group, right? If you have a swing arm, you can just run it in the other direction, right? If when you're looking at the swing arm and the swing arm sticking out this way, run it in this direction. It's out ahead of the pivot, right? It'll get through everything dry before everything else, okay? So these are just little tidbits you guys can use, take home, and be some irrigation professionals for these guys. But I love this one because not everything is our fault. I heard it earlier today. I think Mike and I were talking about some stuff with the grower. They decided to do something because of misinformation. Lots of data out there to make these decisions on, right? They looked at some satellite imagery. They made a decision to put more water down because the satellite imagery was showing them weak plant health. But it's a low-lying area. Why was that plant health weak? Because it had too much water. But without boots on the ground and people who actually understand how these stuff needs to work, they decided to put more water on there. They caused more problems, right? So just my only suggestion here for all this stuff is just make sure we're irrigation experts, not just water managers, not just pivot dealers. When we become irrigation experts, we can really help solve problems for most growers. So like I said, just a little recap. We've covered the operation, sprinkler design, very high level pumps, and identifying infield issues. My suggestion is for everybody, I'll be around all week. If you guys have any questions, I'll help answer everything. But also there's Reinke dealers here. They're probably better at this than I am. Some of our TMs are here. If you guys have any irrigation specific questions about pivots or laterals or anything in general, just feel free, come find us. We're always here to help. And with that, I think I'll kind of open it up for questions if anybody's got any. Like I said, they said, can you talk about pivots for half an hour? Sure, we'll try to jam it all in here, right? Yep. Sorry, go ahead. Ask the question again.
Do you account for wear and tear?
Do we account for wear and tear on pumps when we're designing them? No. Let me give you a good example, or let me give you a good reason why. If I'm going to design something to operate 20 years from now when that pump degrades, I've now ran 20 years of an inefficient application. And when we're starting to talk about fuel cost, water management, water's being restricted. I would hate to not do everything upfront as quickly as we can, as good as we can. So
Put the gated.
now some things we want to think about is water levels, right? That's other things you got to take into account, but that's other things. Any other irrigation pivot questions? I don't know how we're doing on time, Nick.
We're doing perfect.
Yeah. Yeah, sorry, Mike. I forgot. I took notes that Nick and Rebecca were throwing me under the bus earlier. I was going to hit all those before I even started talking. One of the questions was, compaction rates with water droplet size and everything else. Honestly, that only takes place 2 times. One, if you're pre-irrigating, right? Bare soil irrigation or post-irrigation. Okay? If we're irrigating raw soil, right? Bare soil, then yes, we definitely need to consider droplet size, all that kind of stuff. And there's all sorts of options out there about how we manage that part. But some other things that will help with that, cover crops, right? If we can get any plant interception to take the energy away from that water droplet, but it still goes where it needs to, that's a lot of things that will help out. But when you get into some of those, specialty crops, you get into, I know some, I don't know if anybody around here has carrots in their area, right? To germinate carrots, it's a real challenge to do with pivots, right? Those water droplets hit that, and I don't know if anybody's ever seen a carrot seed. You can have about 1,000 of them in your hand, blow real hard, and they just go all over. So a lot of that really depends on crop type and understanding and having those conversations up front before we know what we're going to do with sprinklers or irrigation equipment. So any other questions?
Very good. I don't think we have anything else, but we'll take a 10-minute break. I appreciate Jake for sharing all of his knowledge.